I'll start recording again. So we're picking up with the new lecture 5. So the question was about using likelihood ratio tests to judge contributions to the model. Yes, as long as you are in maximum likelihood, regular flavor maximum likelihood, you can do any kind of nested model comparisons you want via likelihood ratio tests. You can change what goes into the variance or the distribution. You can change what goes into the slopes. You can do anything. If you are in residual maximum likelihood, so what is known as either residual maximum likelihood, restricted maximum likelihood, or abbreviated REML, R-E-M-L, then you cannot. And so that's one of the reasons why I don't teach adding slopes and checking likelihood ratio tests, is because it does not generalize to all the different kinds of models that you would work with. And to avoid that source of confusion, I tend to favor walled tests, so lumping the slopes together and getting an F or a chi-square within the model, because you can do that anytime you want. You can only sometimes do likelihood ratio tests to judge the addition of new fixed effects when you're in regular flavor maximum likelihood. And that is when you are fitting any kind of generalized model. There is no such thing as REML for generalized models. And any kind of model that has a latent variable in it, for the most part, that's estimated with measurement model type software, so structural equation models, item response models, factor analysis models, that's regular flavor maximum likelihood too. Okay. Other questions? Are we ready for something new then? Yay! Can we get some fake enthusiasm?
I'm enthusiastic.
Yay! Yeah. So multivariate models. So this was, I had a really fun experience. Thank you. That was some very nice manufactured enthusiasm, Zoomers. I like that. I had a really fun experience teaching these models because it was something that I had learned 10 minutes ago when I was a postdoc. And what happened when I was a postdoc is that everyone at Penn State in the Human Development and Family Studies area where I was focusing, who taught methods courses, decided to go on sabbatical or take grant buyouts the same semester, and they were going to have no courses. So they let me teach because it was like literally better than nothing. So the first course that I ever taught in my life was a course on multi-level models that I had just learned 10 minutes ago. So, you know, as you can imagine how well that went. But one of the things that I taught in that course was multivariate versions of the models. And there were a whole bunch of students in there that were like, oh, you can do that? And I just made their day. So this is one of those things, too, that I feel like is sort of under the radar with respect to how you can answer questions in multivariate context. And this falls under a lot of distinct categories. So the first part of what I have here is literally just trying to map choices, vocabulary, and designs and things onto each other so that you can know what situations what we're going to talk about is applicable for and what situations it's not going to be applicable for. And then, how do we make it happen in software? There's sort of two ways to do it, and one way is a lot less flexible, but easier to potentially get started with. And so we'll actually end up seeing both ways. So here's the show then. So multivariate dependency, options for software, options for how we're dealing with the multivariate dependency, and then options for specifying fixed effects. So back to this slide again, where we've been so far. In talking about general and generalized linear models, we have three pieces to consider. The link function, which is necessary whenever you have outcomes that have boundaries and you want to make sure your predicted outcomes stay in the boundaries. If you are fitting a just standard ANOVA regression type model, what's your link function? Identity, which means what?
Times 1.
Times 1, right. So that's why general linear models are still considered part of generalized because of that simplification. Linear predictor, this is the part that is the same no matter what. And so one of the things that I hope to convey to you by the end of the semester is that the strategies that you think of for how do you put predictors in a model, you know, do you treat them as quantitative variables and estimate a slope? Do you treat them as categorical variables and estimate dummy-coded slopes? Do you think of them as hurdle, if and how much, combinations? All of that is completely agnostic as to what kind of outcome you're predicting. So the principles of linear models and how to think about slopes and interaction terms, that is constant across all of this and across everything you would do with latent variables as well. Now you will hear me in this unit start to change how I talk about things. So I'm trying to give you a heads up here. The model that has the fixed effects, that part of the model, I will refer to that as the model for the means, because that's the part of the model that deals with how each person gets a conditional mean given their predictor values. So this is terminology that I introduce more specifically in any of the multi-level classes, but you will hear me start to slip into that phrasing. The third part about it then is how the outcome residuals should be distributed given their possible values. So the reason that in generalized linear models that we work with normal is because those are outcomes that are supposed to be continuous. They're supposed to be symmetric and continuous such that a normal distribution is a good fit. But if that's not the case, then we have a whole bunch of choices, right? We've got binomials, we've got Bernoullis and multinomials and beta binomials and Poissons and all kinds of stuff. So here's a new part then. If we are dealing with a situation where residuals are likely to be correlated, the term for that is dependency. So the residuals are dependent across observations. Just think correlated. And the reason for that is related to your sampling. If you collect multiple outcomes from the same person, odds are really good that the residuals from those outcomes from the same people will be related. If you collect multiple outcomes from the same intact unit, like a classroom or a clinic or a TA who's supervising a course, who's in charge of grading, observations that are collected from that same unit are going to be related. So this idea of dependency ties almost directly into your dimensions of sampling that created your data set in the first place. So this is the additional part that we have completely ignored up to this point in this class, because all of the examples that I've given you are using independent samples. Cross-sectional data, one per person, and no other higher level sampling structure that would cause additional layers of dependency. So now we have to figure out how to adapt the model for situations in which we have some kind of pattern of dependency. And you will start to hear me lump together this idea along with the conditional distribution as model for the variance. So these are not choices about what kind of predictors you put in or whether your predictor slopes should be main effects or interactions or any of that. That's fixed effects and model for the means. What I'm talking about, what makes this unit different, is this idea of modeling covariability in your residuals. Okay, with me so far? All right. So, situations in which you would have to worry about dependency. Dependency is the statistician version of a problem, but to some people, dependency is the whole point of their study. So the people at Penn State that I work with, the students there in the Human Development and Family Studies, Sciences, I forget what the S stood for, they were focused on adult development and parent-child relationships and all kinds of things like that. So the bread and butter of their research designs were deliberately sampling multiple members of the same family. We would get opinions about how mom views the relationship and how dad views the relationship and how the kid views the relationship. And we would look at the correspondence between those two, as well as like if the mom's stress level affects the dad's relationship satisfaction, and if the dad's stress level affects the mom's relationship satisfaction, those sorts of I'm going to make this symbol. For those of you on the YouTube, I'm making an X with my hands because this is often described in a framework known as actor-partner models, where you have straight paths between the predictors and outcomes that come from the same person, and these are like the cross paths of person A's predictor with person B's outcome and vice versa. So this was the part where they got really excited, because the students in those sorts of designs had gotten used to here's my model for all the mom outcomes, and here's my model for all the dad outcomes. And they didn't know how to put it together so that you could have one predicting the other at the same time. So dependency is either a problem to be solved or the whole point of your research design. So we are deliberately hacking the idea of dependency in repeated measures designs, because if you can hold each person as their own control, you get a more powerful test of whatever intervention or manipulation that you're doing. If you can collect people from the same group or cluster, so in school research, oftentimes you'll have student level information, teacher level information, and if you're sampling multiple schools, school level information, and all of those things can predict each other or be outcomes at each level. So most of the data, I'd say, that we see in real life has some kind of dependency. It's actually pretty rare that I ask somebody about their data and there's nothing that would have any kind of correlation whatsoever. So in terms of modeling strategy, though, one key distinction as to how you would go about putting all of this information in the same model and building in residual correlation is whether the data can be described as balanced. Now, what I mean by that is that there is a common set of possible outcomes. Now, some people could be missing certain outcomes, but there's only so many. So if I have, say, a repeated measures design where I spend time in condition A, and then I spend time in condition B, and then I spend time in condition C, my outcomes from A, B, and C are going to be related. But I would likely need to have one source of residual variance for everyone's performance while they're in A, another source for everyone's performance while they're in B, and another for when they're in C. And those are differentiable. And I would have research questions about how A and B differ from each other, and B and C differ from each other, and that kind of stuff. But there's only 3 possibilities. Alternatively, if I had something like a daily diary study where I ask people every day for a month to answer some questions, the number of days per person and which days of the week they fall on, that could all be different. And so when you have like a different set of possible outcomes, I would call that unbalanced. Likewise, if you go into schools and you sample multiple classrooms, the data are unbalanced if there's a different number of kids per classroom. So what we're going to cover in this class is exclusively focused on balanced data. So when you have a multivariate setting where there is a finite set of different outcomes per sampling unit that you all want to predict at the same time. If you want to learn about unbalanced data, come back. So that's what the clustered multi-level class or the longitudinal multi-level class, respectively, will talk about. Question?
Would considering unbalanced data be a solution to missing data?
It depends. So like in the example of, conditions A, B, and C, I don't have to have everybody be in all 3. Like if you only did A and B, I can keep you so long as we're using likelihood estimation. The difference would just be like the number possible and whether that number possible and the structure of it is the same across people. If I had a study of like pre-test, post-test, and follow-up, that's balanced. Okay. Does that make sense, the distinction?
Yeah.
Yeah. If you have a test and everybody answers questions 1 through 10, that's balanced. So there's a lot of situations in which everything is sort of neatly arranged and balanced, but then in more realistic sort of observational designs, you can head into unbalanced territory. So we're staying with balanced for right now. In terms of how to estimate these models, I'm going to show you 2 different approaches. One is by tricking univariate software. So the same routines that we have seen in pieces like Glimix and Mixed and SAS and in Stata, and in R it's going to be a routine called GLS within the NLME package, that those are set up to look like typical regression models where you have one column and that's your outcome. You can trick those types of software into estimating multivariate models, and I'm going to show you how to do that. When would you want to do it this way? anytime that you would think about doing a traditional repeated measures analysis of variance. So if you're interested in mean differences across your outcomes, if you want to know if people do better when they're in condition B than condition A, univariate software allows you to put in which condition is which as a predictor and directly answer that question. So it maps onto linear models in the way that we're used to thinking about them beautifully. If you're interested in testing whether the effect of a predictor differs across outcomes. So let's say that you also let people do different amounts of practice, and you want to know if the amount of practice someone does matters more if they're in condition A than when they're in condition B. If you want to know whether or not an intervention is more effective at reducing anxiety than it is at reducing depression. So questions about how slopes work differently across repeated outcomes from the same sampling unit, that would typically be analyzed by what's known as a multivariate analysis of variance, or MANOVA. We are functionally going to do that, but with likelihood estimation. So this is all super cool, so long as you're in general linear model land. But what I discovered the last time that I taught this class is that the options within this framework for generalized models kind of suck. What's going to end up happening is that in order to fit multivariate models with univariate software where all of the outcomes have to be stacked into one column, is then that column only has a single, say, stretchiness factor estimated for it if you have a negative binomial. Or if you have a cumulative ordinal model, you only get different submodel intercepts for one of your outcomes and not the others. So there's these weird limitations and flexibility that come from the data structure in this context. And so if you're in generalized models, I probably wouldn't do it this way. I would do it a different way, which is to treat them as multivariate analysis via path models. So path models, or path analysis as it's known, is a framework for doing a whole bunch of regressions simultaneously. So there's no trickery involved. It just all happens at once. And to do this, you will need to learn how to use software that also is capable of estimating structural equation models. So for that reason, path analysis is often taught within courses on SEM. I do not do that. I made a deliberate choice to separate the two because structural equation models is all about using latent variables to measure constructs more reliably and to look at relationships among those latent constructs, which is a different ballgame than path analysis, which is just multiple regressions at the same time. So we're doing path analysis in this course, but if you stick with me for the fall to do SEM, they will show back up at the end of that course as well. So when would you need to do path models instead of tricking univariate software? Pretty much anytime you have a generalized model, but also situations in which your research questions dictate that a given variable is both a predictor and an outcome simultaneously. So when would that happen? The classic example is mediation. So if you have a hypothesis, say that treatment condition, treatment versus control as my X, is going to help differentially improve parent whatever, and improvements in that parent whatever are going to trickle down and improve child whatever. Something like that, where you think that really the reason between X and Y is because X fixes M and M fixes Y. To answer a question about all of that simultaneously, you have to find a way to estimate regression models in which M is allowed to be an outcome with respect to X and simultaneously be a predictor with respect to Y. It is possible to do that via separate general or generalized linear models, but it's kind of clunky. So I want to show you a way to put it all together via path analysis. The big difference here. So there is a reason also why in the introductory stats class, intermediate as it's currently called, I don't do anything repeated measures, is because listwise deletion. So if you're stuck with ordinary least squares estimation, sums of squares model, sums of squares residual, all that crap, remember that? The thing that we haven't talked about this whole semester? If you are using that to estimate your model, then anybody who is missing anything is kicked out. It's known as listwise deletion. Likewise, what most people think of as repeated measures ANOVA forces, without testing, all conditions to have the same residual variability and covariability, which is usually not a reasonable assumption. And the reason that that is required, again, is least squares estimation. So we're doing the same kinds of analyses that would get taught in sort of a classic multivariate class, but we're doing it with likelihood estimation so that we can use whatever outcomes a person does contribute. And the assumption that we're making about the missing data is then missing at random as opposed to missing completely at random. So it's a more, what's the word I want? It's better. How's that? It's just more better. Missing at random versus completely at random, are these words we've talked about in here? Maybe? I forget which class I've talked about things in, so.
I don't think so.
Not yet? Okay. Very briefly, missing completely at random is exactly what it sounds like. That what people would have told you has nothing to do with anything. So if you are handing out like paper surveys for a research study and the copy machine each pays 5 for some of your people and you don't realize it until you're afterwards, and so the people who had that copy of the survey don't have a page 5, that's missing completely at random. Like there's nothing about them that caused them to not answer the question. Missing at random is what everything with likelihood estimation assumes. It is not testable because you are lacking the data needed to test it. So this is a favorite thing for reviewer 2 to complain about because they know they can't answer it. You cannot test for missing at random. It is not possible. What it means is that there is a reason for the missingness. So what they would have said is informative, but you got it covered by the information you do have about them. So like if the questions on page 5 were like, how much money do you make a year? And someone's like, I'm not answering that. I'm not going to tell you how rich I am or how poor I am. But you have their address. You have their education level. You have other things about them that would be related to their income. The assumption of missing at random means that it's conditional on those values, then it's missing actually at random. So in this context, let's say that I have my repeated measures design where I'm providing data under condition A, condition B, condition C, and I don't get condition C done. Well, to the extent that how I would have done is related to how I did do on A and B, and you've got that, then that's missing at random. So it's the idea of using all the information that you do have with respect to their either other outcomes or their predictors to condition and try to come up with what the answer would have been for your parameters had the data been complete. So anything with least squares and dropping people is a missing completely at random assumption, because once you work on a subset of the data, it doesn't know what's missing from it. The idea of likelihood estimation is to recreate the model parameters that would have been there had the data been complete, even if it's not complete. In medical settings, it's also known as an intent to treat analysis because you're not kicking out the people who didn't complete whatever the process was.
How accurate is that?
I don't know. I can't know because I'm missing the data needed to test it. Question. Would definitely be interested in taking a course on missing data. Yes. There should be a course on missing data. I find it unlikely that that will happen in the next 5 years. It's a degrees of freedom problem with respect to, even though our program has 10 faculty, there are only 2 of us who are 2 and 2. Everyone else only teaches 1 or 2 courses a year. And we have to cover undergraduate level courses as well as graduate level courses. And so that's where the lack of degrees of freedom comes from. But I agree, a course on missing data would be a great idea. Question.
So you use maximum likelihood to predict data that is missing, and then you use Bayes if maximum likelihood doesn't work for that.
Bayes also addresses missing data by filling it in, essentially, at each imputation.
But it's based on like what you assume to be true.
Yes.
Okay, and that can be problematic if it's biased.
It's all based on that. How do I say this? I have a couple slides on this, but since we're on the topic, the idea at the core of it is that, yeah, it's going to take a while. Each person has a likelihood function. Like if you picture your own little mountain, that describes the likelihood of not just one outcome as it has been, but all your outcomes together. So rather than it forming a point, it forms a function. The assumption is basically that the shape of that function would be the same whether you have all the points contributing to it or not. So if you think of it like in a growth context, let's say that you're measuring decline over time and people who decline a lot end up not coming back to your study. The assumption of missing at random would be like the slope is correct because the observations that you don't have would have followed the same slope. But like if they just fell off the cliff instead, you wouldn't know that.
That seems problematic.
It is problematic, but you don't have the data. Like
yeah.
there's nothing that you can do from the perspective of solving it. Throwing in anything that would be related to why you don't have the data. It's very different, say, like if a kid dropped out of high school versus moved out of the district and you don't get to study them anymore. Like those kinds of things. You can put in any information that would be related to missingness to help. Multiple imputation is the other way that people address missing data, which is making up fake data, which sounds like cheating, and it sort of is a little bit, except that you do it by adding error terms to it, and you do it lots of times.
Is that MCMC?
MCMC is Markov chain Monte Carlo, which is not the same thing.
Okay.
It's in the same like family, though, of ideas. So multiple imputation would be like, you try to predict what a variable is in your data set from all the other variables in the data set, but you can't just put in the prediction, right? Like, because then you're cheating, because you don't have that perfect on the line prediction. So you add an error term. And you do that like somewhere between 5 and 100 times. It used to be 5, but now that computers are good, you can do it like thousands of times in a second. And then you run your analysis on every single completed data set separately, and then you aggregate all the results together with formulas that allow for between imputation variance to contribute to the standard error as well as the original standard errors within an analysis. Now that sounds like a very giant pain in the ass, but most programs have a way to do it for you. So like in M+, there's a type equals imputation that will run all the models, generate all the results, and put it all back together again. And I'm quite certain that in R there's a way to do that too.
It's so fascinating. I wish there was a course on.
I know. Sorry. Not it. That's just what I'm going to say. Not it. You know how many different courses I've taught since I've been here? Like 6. That's enough. Not it. Talk to someone else about that. But by the way, the third category is either missing not at random or not missing at random. The not part gets rearranged depending on who you read, and that's exactly what it sounds like. Like, yeah, it's not random, but we don't know. And guess what you can do about that? Nothing. Yeah. The answer to that is to try to build something into your model that is the reason why you have missingness that way, and then see what happens, and then maybe do a different model with a different reason and see what happens. Yeah. So there's not great answers because you don't have the data.
Sounds like a dissertation topic.
Oh yeah, missing data is a very active area of research. So certainly could be a dissertation topic. It has been many dissertation topics. Anywho, that is the big difference between sort of the classical techniques. Like if you learn what people would call MANOVA or repeated measures ANOVA, when they use those words, they mean least squares, estimation, kick out, incomplete cases in most of the time. So there's nothing wrong with those models as models. The problem comes in the use of least squares to estimate it, which requires you to dump cases. The other piece is that traditional repeated measures ANOVA only has two choices for the type of dependency that you can have, whereas modern approaches to longitudinal data, of which repeated measures would be a one subset, there's lots and lots and lots of choices. So the choices within traditional approaches that use least squares are limited because they use least squares. So we're doing everything with likelihood so that we've got maximum flexibility. All right, but not today, because it's 1:43. All right, any questions before we call it a day? All right, well then it's Thursday. That means I say have a good weekend. Homework's due on Monday. Let me know if you need anything. Otherwise, thanks for being here. See you next time. Peace out.
Do the concepts around missing data change for latent variables? Like latent